Welcome everybody to this second session on hybrid methods. Our first talk will be on conflict-free learning and for mixed integer programming by Jakob Witzig and Timo Berthold. So I don't know who starts speaking. Good.
Good morning, good evening, good afternoon. Welcome everybody to my presentation on conflict-free learning. This is joint work with my colleague Jakob Witzig, formerly from ZIP, now at SAP. Conflict-free learning is a variant of conflict learning for situations where a conflict has not yet occurred. As a motivation for this talk, consider the following situation. You solve a mixed integer program, but during the course of the solution process, constraints might be tightened. Only tightened, never loosened. Hence, it might be that subproblems become infeasible after they have been processed. The question that we were asking ourselves is, how can we extend conflict learning from the case of learning from an infeasible subproblem to the case of learning from a feasible subproblem, under the assumption that it might become infeasible later? For this presentation, we will consider general mixed integer programs in inequality form, minimizing an objective function C transposed X. Some of the variables are assumed to be integer, and variables might have explicit bounds but can also be unbounded. Further, as mentioned, we allow that the right-hand side B might be tightened at any point in time. You might wonder what the motivation for this last condition is. Where does such a setting occur? Well, one could certainly come up with specific applications where this makes sense. But there is one super generic application, and this is the so-called objective cutoff constraint. During the course of a branch and bound algorithm, this constraint bounds the objective function which is optimized against the value of the incumbent solution, hence the best solution found so far. In the beginning of the search, where no feasible solution is known yet, the right-hand side, the so-called cutoff bound, is infinite. Otherwise, it is the objective value of the incumbent solution, potentially adjusted due to numerical properties like a greatest common divisor of the left-hand side C transposed X. So, if we assume that the cutoff constraint is part of the constraint matrix, then once a new incumbent is found, the right-hand side is tightened and every subproblem with a dual bound larger than the cutoff turns into an infeasible subproblem a posteriori. Here, we visualize this situation. The cutoff constraint is part of the constraint matrix, but inactive in the beginning. During the search, the cutoff constraint gets tighter and reduces the feasible region whenever a new incumbent is found. Now assume we process a subproblem that we derive by branching on one of the variables. On the slide, you see the branching as a brown line and the current state of the cutoff constraint as a light blue line. The subproblem is feasible for the incumbent known at the point when we solve the subproblem. Thus, the branch and bound algorithm will simply continue branching. However, the subproblem might become infeasible later when a better incumbent is found. In this situation, it will traditionally just be pruned without any further processing of the local information from that part of the tree. This is the setup we came from. Note that if we had just processed the tree in a different order, we would have found this local infeasibility while processing the node, and we would have generated conflict constraints from it, potentially. We wondered whether we could still get hold of these conflicts, even though we detected the infeasibility only later. Therefore, I should say at least a few words on conflict learning in mixed integer programming. In MIP conflict learning, there are two main approaches. The first is to do conflict graph analysis and works very similar to no-good learning in ZAT and CP. It is a combinatorial approach that keeps track of bound implications throughout the search. The second is dual proof analysis, which is an analytic approach. It derives a globally valid constraint from the dual solution of an infeasible or bound exceeding LP solution. For our work, we focused on this latter approach that uses the dual solution. The dual solution of a linear program is a set of non-negative multipliers which we can use to aggregate the original constraints. This will again give a valid constraint that underestimates the objective. This is why it is used for bounding. This aggregated constraint is valid because it is a non-negative combination of valid constraints. Note that for an infeasible subproblem, this aggregated constraint will prove infeasibility. Hence, it is called dual proof constraint. If the cutoff bound has a non-zero dual multiplier, the dual proof looks as indicated in the last line of the slide. Here, A' and B' represent all the other constraints of the MIP. This convenient representation means that we can update the right-hand side of the dual proof constraint later on, while keeping all multipliers unaffected. If you always change the right-hand side in such a way that it represents the objective value of the current incumbent, this constraint will stay valid. It is really just the rightmost entry, C bar or C tilde on the slide, that we need to update. Everything else stays the same. This also means that we can explicitly compute a threshold value for C tilde, from which on it would have sufficed to prove infeasibility of the subproblem from which we generated this constraint. Note again that this constraint is nothing else than the dual proof of a local AP relaxation, hence the AP rows aggregated by the dual multipliers. Essentially, the idea of conflict-free learning is to keep such dual proof constraints when they are promising to give strong propagations in the remainder of the search. This we judge by how close they were to proving infeasibility of the current node. In practice, this requires some amendments to the conflict learning procedure. Usually, we would apply conflict analysis only at infeasible leaf nodes. However, we could run the same procedure for every feasible LP solution as well, and generate a redundant constraint, a dual proof constraint. We've already seen that these constraints can easily be updated and even be sorted by the primary objective value at which they would have pruned the node at which they were created. One interesting side effect is that the derived constraints typically depend less on local bound changes, since they were not necessarily created at leaf nodes, but at inner nodes, higher up in the tree. There is another very related procedure that we call AP-based solution learning. Indeed, with some amendments, you could see it as a special case of conflict-free learning. AP-based solution learning considers MIP-feasible nodes. The cutoff bound can be updated for two different reasons. One reason is that primary heuristics find a new incumbent. The other, in our context more interesting one, is that we find a new incumbent solution because the AP relaxation of the current subproblem is integral, hence feasible for the MIP. Of course, in this situation, the current node will also be pruned, and every following node with the same objective will also be pruned. The same argumentation applies. If we had known the solution before, we would have applied conflict analysis at this node. Hence, we can also apply it in the situation when we find the solution. Note that here, we can easily apply conflict graph analysis as well. We are just not asking why did this series of bound changes lead to infeasibility, but why did it lead to feasibility? Or rather, why did it lead to this objective value, which from now on is not interesting for us anymore. Conflicts and dual proof constraints derived in this way can be readily added to the conflict and dual proof pool of the solver. Within our implementation, we apply AP-based solution learning to every new incumbent that we find through a node AP relaxation. This also means that we apply it only to node AP solutions, not to heuristic solutions. Heuristic solutions often do not use the current local bounds, and they often come without dual information. Hence, they cannot be used for learning. For solution learning, we apply both conflict graph analysis and dual proof analysis. Maintaining all potential conflict-free proofs can produce a significant overhead. Thus, we store only some and apply a filtering mechanism to predict which are the most promising ones. This filtering relies on two main characteristics. Firstly, the primary bound for which the constraints would prove infeasibility. The larger, the better. We prefer constraints which are close to proving infeasibility. Secondly, the number of non-zeros. The smaller, the better. Note that for conflict-free learning, we only conduct dual proof analysis. We implemented both procedures within the constraint integer programming solver SCIP and conducted a computational study on the benchmark set of MIPLib 2017. We used 3 different random seeds to counter the effect of performance variability. In our computational study, we compare 4 different settings of the solver. Default, hence without any of the techniques, conf-free, for only applying conflict-free learning from inner nodes, and soul learning for LP-based solution learning. Finally, we tested a fourth setting, where we applied both of them together. Here you see the results of our computational studies. The rows of the tables read as follows. All refers to all instances affected to those instances that could be solved by at least one solver, and where the solver took a different solution path between at least two settings. Greater equal 100 seconds means that at least one solver took more than 100 seconds. The columns show S for solved instances, T for time, and N for nodes. For all but the default settings, we show factors for time and nodes instead of absolute values. This means a factor less than 1 is good because it shows an improvement, and larger than 1 is a deterioration. We see that with both conflict-free learning and solution learning, we can significantly reduce the average search tree size. However, the impact on solving time is much less, at least for conflict-free learning. This is because the procedure introduces an overhead on storing, maintaining, updating, and so on. Both techniques work particularly well for pure binary and mixed binary problems. This is partially because those are the more combinatorial problems, and partially because conflicts for general integers are intrinsically weaker in MIP. For general MIPs, we can observe up to 2.5% speedup on affected instances. For binary problems, it is around 5%. Note that the combined approach is slightly less efficient with respect to time, but the most efficient with respect to the number of branch and bound nodes. To summarize, we introduced the idea to learn from MIP subproblems that are either feasible in that they provide a new incumbent, or at least not yet infeasible. To this end, we presented two new learning strategies, conflict-free learning and LP-based solution learning. We further showed that both of them can help to improve the performance of a MIP solver as an extension of the traditional dual-proof learning scheme. With this, I would like to say thank you, and may all your optimization problems solve nice and smoothly, without conflicts. I'm happy to answer any questions, live here or in a separate Q&A session. Until then, bye-bye. And hello.
Thank you, Timo. Yes, thank you, Timo. Are there any questions? I don't see any in the chat. All right. I don't see any hand raised, so I'll go and ask one. So did you check on using different sets of problems, like problems where feasibility was quite easy and solutions like incumbents were produced at a high pace, whether problems which were where it was harder to identify at least even one feasible solution?
Mm-hmm.
I will take this one. Yes, we did this not for this experiment, but we did a similar experiment for a paper we have written before. So with the amount of solutions, so this is a very tough experiment because this highly depends on the solver in the end. And if you find a lot of solutions in the very beginning, then the techniques in the end will not work anymore. And if you find in the very end, then they will also not work. So you need a solver that finds the solutions somehow distributed along the whole solve. And this is something that usually does not happen and would be a very special setting. So we did not run this experiment for this particular setting here.
Thanks. There's another question from the chat. Would it make sense to just add the constraints obtained by the dual as a learned constraint instead of waiting until it becomes conflicting?
So yes, actually that's something that we do here. So we add it, so to say, shortly before it becomes conflicting, when it's only a few % away. So adding it just right in the beginning when it's far from conflicting is too early, so propagation then slows down. But we found that adding it slightly before is already beneficial. So yes to that question.
Okay. I don't see any hand raised or any other question in the chat. So I guess we will take this 1 minute to try to catch up the schedule and move on. So if you have any more questions, you can go in the individualized Q&A. Later in the coffee break.
Yeah, see you there.
So let's go. Thank you again, Timo and Jakob. we'll go to the second talk, which will be on exact methods approaches for the differential harvest problems by Gabriel Volte, Eric Bourreau, Rodolphe Giroudeau, et Olivier Naud.
Hi everyone, my name is Gabriel Volte and I will introduce you my work on the exact method approaches for the differential harvest problem. So in few words, what is a differential harvest problem? You have a vineyard with two grapes quality, here in green and red, and we want to harvest all the vineyards and harvest separately good grapes quality. We want to do that with minimizing the total harvesting time. And to do so, we have the following harvesting machine. So this is special harvesting machine with two harvesting modes, which I will come back later. This machine has two hoppers with a certain capacity. And the low turning wedge, which give us a non-Euclidean distance matrix. We can't stop in the middle of a row, so to empty the bin and come back later to finish harvest this row. This means that you can only harvest the row if you have enough capacity in both hoppers, and when either hopper is full, you have to return to the bin to empty the hoppers. So for the vineyard representation, we choose A and B to be the two grapes quality, and we assume that A is a good grape quality. And for the selective mode, we have the non-selective mode and the selective mode. For the non-selective mode, we do not sort the grapes quality, and so the A and B grapes can be harvested in both hoppers. So it means that the harvesting is balanced between the two hoppers. So here there is no problem. But in selective mode, the big grapes can only be harvested in one of the two hoppers, and the hay grapes can be harvested in both hoppers, but we want to harvest it separately, so we only consider hay grapes to be harvested in the hopper with the big grapes only when the first hopper is full. So we do not want to corrupt hay grapes with big grapes. And additionally, we have a technical issue with this machine. It occurs in the selective mode, and the key point is that we do not want to corrupt A grapes with B grapes, and it occurs only after BA transition. So for example, in this row, we are going from an A zone to a B zone, and we can harvest 50 A grapes and 50 B grapes with no problem if we switch the hopper as soon as we enter in the B zone, and we do not corrupt no grapes at all. But in the other direction, we can see that if we change as soon as we enter in the A zone the harvesting hopper, we can corrupt A grapes with the residual B grapes stuck in the harvesting machine. So we have to wait until the machine is fully in the A zone to harvest in the hay hopper. So here we assume that we lost 5A that is corrupted in B grapes. So in this direction, we only harvest 45 A grapes and 55 B grapes. So the harvesting is not symmetrical, it depends on the direction. For the description, we choose to switch for the real description in which we consider extremities of the row to the rows itself. And to do so, we just merge the extremities in one vertex, and we add a label on edges to consider the direction. And for the exact approaches, we use column generation with parse animation technique, and the principle is the following. We solve optimally the column generation, and to obtain an optimal solution, integer solution, usually you also do branch and price, but here we choose to solve a special subproblem which will enumerate all routes with a cost given by an integer solution and the optimal solution for the column generation, which can be non-integer. And then when you solve the restricted master problem using integer programming, you have an optimal solution. For the constant programming, we use the standard vehicle routing problem model for constant programming, and what we did is to implement a snake strategy which mimics shortest path heuristic. This is a construction heuristic which we assume that it will give us a good solution in small amount of time. So for the experimental result, the instances are the following. We consider three types of instances, so G, T, and S. G is real instances located in the south of France. And for this instance, we consider smaller instances with consecutive rows. And the T and S instances we consider they are the worst case instances because everything seems to be symmetrical, which will be difficult to solve for optimization solver. So for the result, for the column generation, we want to see the impact of the Hermine. So when Hermine increases, how behave the CPU time and the objective value. So we can see that the objective value does not change at all between 0 and 90% of Hermine. But when you go from 90% to 100%, the objective value goes up. This is because the direction are fixed, and you cannot choose the smallest distance between two rows to harvest efficiently the vineyard. And for the CPU time, this is the opposite. So now you have fixed all the direction between the rows. The CPU time decreases a lot, and the solution becomes trivial. So here we want to see the impact of the kappa max parameters. So this is also for the real instances. We are able to solve all the instances between 10 rows and 12 rows, but after 30 rows, we are not able to solve optimally all the instances. And we can see that there is a variation between even numbers of row and odd numbers of row. And we have computed the ratio between the solution found, the CPU time found for the instances with Cmax at 900 and 1800. And we have computed the factor of 10.5 times higher. So when we double the kappa max parameter, there is an order of magnitude increase on the CPU time. For the constant programming results, we can see that the snake strategy gives us a good solution in less than 1 second, which is what we wanted. So the snake strategy behaves like we wanted to be. And but we cannot find any proof for instances with more than 10 rows. And that's why we want to see how behaves the hybridization between column generation and constant programming. So for the parametric strategy results, we have already seen the impact on the parameters. And to sum up, we have done a column generation exact approach and the constant programming exact approach. And as far as we know, we are the first to solve the 24 rows instance for the first time, and we want to investigate hybridization between constant programming and column generation. And to enhance the results, we also want to try to use a specific vehicle routing problem solver to have the best optimization method in column generation in the state of the art. And we also want to consider the uncertainty in the data, and that's why we also investigate robust optimization, because there is almost 20% of variation on the data, on the estimation of the data. So thank you for your attention.
Thank you very much. Do we have any question from the room or any hand raised? We have a question from the chat. So how large is 0.08% gap in the real world terms in the quantity of wasted grapes or time?
Can you hear me?
Yep.
I'm not sure to understand the question.
When you report a gap, so how does the gap translates from a relative, let's say 0.08% to
the gap is between the objective function value, which computes the harvesting time for the harvest.
So it's in time, that the objective is in time then?
Yeah, we do not compute the wasted grape.
Okay, and how many minutes is that, 0.08%?
I think it's less than 1 minute.
Yeah, so
it's very small.
Okay, so you mentioned a little improvement when increasing kappa max. Have you looked at other search heuristics?
No, we do not search other heuristics. We have an improvement on the, because for the column generation approach, when you increase kappa max, obviously you the subproblem becomes harder because the Rousseau constraint shortest path problem will tend to generate all routes like almost 9 n factorial routes, which are possible to compute. But we also tend toward the TSP problem, which we do not care about the capacity, and that's why there is an improvement in the objective function. But we do not look for heuristic.
Okay. So I have a quick one. So how often do you need to resolve this, like over the following year? Would the problem still remain the same, or the production changes and that changes everything?
Sorry, can you repeat, please?
Like from 1 year to another, does it change a lot the problem definition? Like if you solve it this year, then you need to solve it again next year.
Yeah, you speak about the estimation of the yield of a field.
Yeah.
Or, actually, this is really hard to estimate the yield of a field, and even harder to estimate the grape quality. So that's why we, at the end, I spoke about the robust optimization to try to have a bit of a counterpart on this uncertainty on the data.
Perfect. Thank you very much. And we'll move on to the next talk. If you have any question, there will be a dedicated Q&A session later on. So the next talk will be on template matching and decision diagrams for multi-agent pathfinding by Jayanth, Krishna, Mogali, Willem-Jan van Hoeve, and Stefan Schmidt.
Hi, this is Jayanth Mogali, and I will be presenting some joint work with Professor Willem van Hoeve and Professor Stefan Smith on template matching and decision diagrams on multi-agent pathfinding. Let me begin by explaining the MAPF problem on the grid world. We are given a set of robots occupying different locations on the grid. We're given a set of goal locations, one for each robot. Between consecutive time steps, a robot can move to one of its neighboring locations or stay in its current location. The task here is to figure out a path for each robot from its start to its goal location and a schedule such that the plans for the robots are conflict-free. A plan is said to be conflict-free if there are no vertex or edge collisions. The objective that we wish to minimize is defined in terms of step costs. A robot incurs no cost for some time step if it is just waiting at the goal location. Otherwise, it incurs a cost of 1. Our goal is to develop a procedure that computes an optimal plan quickly. Prior approaches for MAPF can be classified into 4 categories, namely A*-based methods, CSP solver-based methods, polyhedral methods, and the 4th approach, conflict-based search, in short CBS, is a branch and bound search procedure. Shortly, I will give a high-level sketch of CBS as it is used in this work. In this work, we take a polyhedral view of the MAPF problem, so we need to introduce the variables with which we model the problem. We basically have variables to indicate whether a robot traverses some edge at a given time step in the optimal solution. Now, using those variables, it is straightforward to formulate the MAPF problem as a 0-1 integer linear program. We basically have a constraint to force each robot to plan a start goal path and another constraint to ensure that the plans are conflict-free. I will now explain CBS. So CBS is a branch and bound search procedure, which at the root node omits all the conflict-related constraints, so we are just left with the path constraints. We can obtain the optimal solution to this problem by applying any shortest path algorithm separately for each robot. Now, if the plans generated for the robots contain conflicts, the basic idea of CBS is to branch in one of the conflicts. Successor nodes are introduced into the search tree, where each successor node inherits all constraints from its parents, in addition to a constraint to prevent the previous conflict from happening again. Now, the optimal solution to the MAPF problem can be obtained by expanding the search tree in a best-first manner. Having a good node evaluation function tends to improve the search performance. In this work, we designed a new node evaluation function for the multi-agent pathfinding problem. Now, since our goal is to construct a good node eval function, let us first look at the value that a perfect node eval function must return for some input search node, and let opt denote that value. Now, opt is equal to the optimal objective value to this problem shown. The problem written here is identical to the MAPF problem plus the constraints in that search tree node. Now, a good node eval function is one that is capable of outputting a value that is a tight lower bound to opt. To provide a geometrical intuition for the approach we developed, I will rewrite this optimization problem differently. Observe that the feasible set to this problem is a set of discrete points, where each point corresponds to a conflict-free plan for the robots. So we can take the convex hull of those points, and I represent that with the letter capital P. Now we can rewrite this optimization problem as a linear program over the set P. Now, in reality, we do not know P, so we cannot compute opt using this linear program shown here. Now, to get a tight lower bound to opt, a natural idea is to construct a tight relaxation to the set P, which is shown in red. A lower bound to opt can then be obtained by minimizing the MAPF objective over the relaxation. Now, let me give you a high-level description of the methodology we use to obtain the node eval function. So our function will be obtained at the end of an iterative procedure where we start at a relaxation of P and progressively tighten it by adding linear inequalities, also known as cuts. The procedure that I'm going to describe is referred to as the Lagrangian relax and cut procedure in literature. Now let P prime denote the relaxation that is obtained by omitting all the conflict-related constraints in the problem. Now let's consider the plan that is generated by applying the shortest path algorithm, ignoring the conflict constraints. Assume that the plan generated does contain a conflict. Now the conflict containing plan corresponds to some vertex of P prime. And if this is that vertex, we can generate a cut like this purple line shown here, which separates the infeasible vertex from the feasible set shown in red. Now, consider the problem of minimizing the MAPF objective over the region of P prime that is not cut off by the cut generated. Now, we can obtain the optimal value to this problem by solving its Lagrangian dual using a well-known technique known as the projected subgradient ascent algorithm. Now, during the course of maximizing the dual objective with subgradient ascent, the procedure generates a vertex of P prime at every iteration. Now, some of those vertices may correspond to plans with conflicts. And when that happens, we can generate cuts to separate those vertices from the feasible set. And we can include those cuts into a dual objective, thereby strengthening the dual bound. At some point, we stop adding cuts and just solve the dual problem to optimality. We can treat the objective of this dual linear program as a node evaluation function, where lambda will be set equal to the optimal dual multipliers of this problem. Once we have the optimal multipliers, a node evaluation function is very easy to evaluate. It only requires computing the shortest path for each robot with these Lagrangian arc costs. And so it is computationally cheap. So although I have given this impression that for computing the node eval function, we add cuts at every node of the search tree, in our implementation, we only added cuts at the root node. We simply reuse the cuts and the multipliers from the root node while evaluating every other node. So next I move on to another crucial feature of our approach, that is the problem of cut generation. Often there is more than one cut that can separate a vertex with a conflict from the feasible region. Deeper cuts are preferable because they lead to a tighter relaxation generally. So say we are given a plan with an edge conflict involving the robots as shown here. A trivial cut for this edge conflict is written down here. However, this may not be the deepest cut in all situations. To get a deep cut, our approach is to project out the feasible region and the infeasible vertex onto a lower dimensional space, as shown here. We then compute a separator on this lower dimensional space. Now observe that this green line or this green cut is a deeper cut than this purple line that we had earlier. We developed a systematic way of selecting the dimensions onto which we projected. The idea is to choose variables that are spatially temporally close to the conflict. We obtain those variables by first building a template of some shape. So here's a square template shown in yellow for this edge conflict. Now this template is parameterized by a set of locations, which includes the conflict location, the time interval containing the conflict time, and the robots that are involved in the conflict. Now once we have the template, we can project out the feasible regions onto the space spanned by the variables that can be associated to this template. Computing this projection is actually quite hard, but the structure of the MAPF problem allows us to compute a tight relaxation to this projection through the use of decision diagrams. I will not be able to dwell too much on the decision diagram, so here's a short snippet. The decision diagram is a directed acyclic graph. We constructed a decision diagram to provide a compact representation of the conflict-free robot paths through the template in the form of source sink paths in the decision diagram. This compact representation enables us to compute cuts efficiently. You can find more details about this in our paper. So we performed all our experiments on 4 connected 30 cross 30 grid with some percentage of cells treated as stationary obstacles. The number of robots varied between 30 to 125. We pre-computed a library of 64 different templates to generate cuts. To solve each problem, we allocated 30 minutes. The first 10 minutes was allocated for cut generation, and in the remaining 20 minutes, we performed conflict-based search. Now, during search, we used our node eval function in conjunction with a previously existing state-of-the-art function called DG. In other words, we evaluate each search tree node using both evaluation functions and just took the maximum value. For performance evaluation, we recorded the lower bound to the optimal cost reported by our combination of evaluation functions and the value reported by just 30 minutes of only including DG. This table summarizes our findings for a fixed number of robots and obstacle percentage. Each entry in this table reports the average difference in lower bounds reported by the two approaches on 10 different problem instances. So a positive value in this table indicates our evaluation function combination is stronger. We see a clear trend in the results. When the number of robots is few and or the obstacle percentage is less, then there is not much benefit with our approach. In congested settings, however, our approach seems to be able to make significant gains. Let me give you some intuition for explaining those results in the previous slide. So consider this 3 robot problem shown here. And suppose we wanted to know whether there exists an optimal solution where all robots reach their goal location at the earliest possible time. Now, to answer that question, we probably do not have to simultaneously analyze all paths from start to goal of all 3 robots. Instead, there may be bottleneck regions like the one shown here in yellow, where every shortest path for each robot must pass through if they were to reach the goal at the earliest time. Now, by simply analyzing the portion of those paths within this bottleneck region, we may be able to draw some inference on whether a conflict-free path is possible without the robots waiting. Intuitively, at least, through the use of templates and cuts, this is the kind of inference we are doing. As the percentage of obstacle locations increases, and when the number of robots increases, the chances of the bottleneck region starts to increase. And that's when our approach seems to be the most effective under such settings. So let me quickly summarize our work. So we proposed a new polyhedral approach for the MAPF problem. Our main contribution was in developing a lower bounding procedure using a template-based cutting plane approach. Our lower bounding procedure is not tied to the MAPF objective that is being minimized. We incorporated our lower bounding procedure into a conflict-based search via Lagrangians, and we demonstrated the utility of our approach for highly congested problems. Thank you.
Thank you very much. Do we have a question from the virtual room? In the chat or any hand raised? Okay. I was curious to see if this, like, could you have a real-time version of this? Like if robots are slightly delayed on the plan or something, and you re-optimize from a given solution in a fast way?
Maybe for the smaller problems, it might be possible to use this in a real-time way. Yeah, I mean, I haven't really tried it, but I do see that the smaller problems do get solved very, very quickly, competitive with the other approaches. But maybe or the other way you can think about it is maybe to just somehow, even if you're solving a very large problem and you see that only a small set of robots are actually congested or stuck, or something happens, some breakdown happens, then you might want to just apply this algorithm to just those set of robots. Maybe that's possible.
Thank you. So there's a question from the room. Is the cut based on the projection guaranteed to be tighter than the cut on the original space?
So I replaced the cuts from the decision diagram using just the cuts from the MAPF formulation. That is, the original MAPF formulation contains conflict cuts based on just pairs of robots. So when I did the comparison with the cuts from the decision diagram versus the cuts from the MAPF formulation itself, I found that the cuts from the decision diagram tend to produce better lower bounds. So so I guess the relaxation seems to be tighter.
All right, any other question? All right, then I suggest we go on to the final talk of this session, which will be improving a branch and bound approach for the degree constrained minimum spanning tree problem with LKH by Maximilian Thiessen, Louis Quesada, and Kenneth and Brown.
Hi, my name is Max. This is joint work with Louis Quesada and Ken Brown from University College Cork. I'm from the TU Wien and was formerly at the University of Bonn, where most of this work happened. Improving a branch and bound approach for the degree constrained minimum spanning tree problem with LKH. We introduce a new CP approach which combines branch and bound search and an adapted local search for the degree constrained minimum spanning tree problem. We achieve competitive performance to the state-of-the-art CP approach and even find near optimal solutions faster than the state-of-the-art approach. To motivate this problem, let us look at wireless sensor networks. The goal here is to establish the communication between the sensors, between the sensor nodes, which might lie in some rural area. You want to find a low-cost way to connect the sensor nodes between each other and also to the sink where the data is collected. And this typically leads to a spanning tree connecting the sensor nodes. So communication protocols often use a spanning tree. But the story doesn't end here, because in various practical settings you have upper bounds on the vertex degrees, which is simply the number of neighbors each vertex has. There might be various reasons for this, so the sensor nodes might have bounded number of radius or limited storing capacity, or in the rural setting you might have battery-driven sensors. And of course you might have efficiency bottlenecks, and you want to tackle all those four problems with upper bounds on the vertex degrees. So let us inspect one typical use case in more detail, and this is the so-called converge-cast process, where you want to collect the data of all sensors towards the sink. And the goal is to minimize the overall transmission time. The catch is that each sensor transmits its data only after it receives the data of its children. And some studies have shown that you can improve the quality and efficiency of this network by constraining the number of sensors that rely on each other. So in other words, by upper bounding the vertex degrees. There are, of course, various other application areas like cyber-physical networks and software-defined networks. If you're interested in those, you can check our paper. Let us now formally inspect the problem. So you can model the task as a graph with weighted edges, and you're basically interested in finding a minimum spanning tree like here. So you take the 5 cheap blue edges and end up with a spanning tree of cost 5. If we now enforce each vertex to be connected to at most 3 neighbors, we can't use those 5 edges anymore, and are forced to use 2 more expensive edges, leading to a degree constrained minimum spanning tree of cost 7 here. Formally, we're given a graph with edge weights that are positive integers and degree upper bounds for each vertex. The goal is to compute a spanning tree which respects the degree upper bounds. So the delta is simply the neighbors of the vertex, and overall we want to find such a tree, of course, of minimum total weight. This problem is NP hard as it subsumes the path version of the TSP, the traveling salesman problem. The nice thing is, this problem is easily modeled as in a CP way. So you have a cost variable z which you want to minimize, and a graph variable g and degree variables d. You use the weighted spanning tree constraint to enforce g to contain a spanning tree of cost z, and then you simply add the degree upper bounds by setting the degree variables d to the actual current degrees in your graph, vertex degrees in your graph, and then you upper bound them by your given upper bounds. The state-of-the-art CPU approach goes beyond this formulation, so they also use a last conflict search strategy which they adapt to graph variables, and a powerful degree constraint with its spanning tree constraint, which is a combination of the mentioned former two constraints. In particular, this constraint enables them to get a really tight lower bound on the cost, and this is the motivation for them to use a bottom-up search, which is the following procedure. So you fix the cost to some lower bound, and then you search the entire search space, and if no solution is found, you increase the lower bound by 1, and then you iterate this process until you find a solution, and by construction this will be the optimal one. The problem is it doesn't generate any intermediate solutions, and we argue that near optimal solutions are really crucial for practitioners. So practitioners are not solely interested in optimal solutions. They often need efficiently computable near optimal ones. Imagine, for example, in the wireless sensor network setting that one sensor node breaks down or its battery dies. Then you would like to quickly come back to a somewhat reasonable working state, and you don't really care in the first place whether it's the optimal one. And we think branch and bound approaches give exactly this flexibility. They can quickly find low-cost solutions, and eventually will also find the globally optimal one. So let us have a look at this simple top-down branch and bound approach. You would find any feasible solution, so any feasible tree, and then post its weight as a cut constraint. And then you iterate this process. So classical branch and cut. The main benefit is you get intermediate solutions, which are hopefully good enough. The problem is you don't have a strong upper bound on the costs, and therefore this procedure, you can suspect it to be slow. This is where we come in. So our main idea is now to improve each found intermediate solution with a local search heuristic, and then post this the cost of this improved tree as a cut, which hopefully then also improves the work of the other propagators and so on and so forth. This general idea was known already a few years ago, but not in this particular setting. We'll use a local search heuristic which is inspired by some popular one for the traveling salesman problem. That is the Link-Carnigan heuristic. It is based on k-op moves for the TSP, where you don't want to find a tree but a min-cost tour, so basically a spanning cycle. And a k-op move is when you want to swap k edges in a way that the graph remains a tour, but the overall cost drops. So here you could swap those two crossing edges with the green dashed ones, and then the cost the overall tour will be shorter. Now LKH is a powerful generalization of those k-op moves. It focuses on so-called sequential k-op moves, which are moves which can be decomposed into sequentially performed 2-op moves, and in various practical settings it finds near optimal solutions or even optimal solutions. And this is the reason why we thought it might be a good idea to adapt it to spanning trees. So given such a spanning tree like here, we want to exchange those two edges in a way that, for example, with those two, such that the overall cost of the tree is cheaper. And of course, we want to not destroy the spanning tree property. This new graph should remain a spanning tree. In particular, you can show that if you fix two edges, then they determine the unique correct swap if you don't want to introduce cycles and break the connectivity. So you don't want to break the spanning tree property, and if you don't want to change vertex degrees. The nice thing is you can enumerate good swaps efficiently with graph traversal algorithms like BFS. This leads to our approach. So basically, simply use branch and bound and then improve every intermediate solution with our adapted LKH. The benefits are it's significantly faster than the simple branch and bound, and it quickly generates near optimal solutions, which we will now show in the experiments. So this is the DE data set where some points were sampled in the plane, and then you take the fully connected graph where the edge weights correspond to the Euclidean distances of those points. And we'll show the runtime here for the three approaches, the simple branch and bound in blue, the state-of-the-art approach in green, and our proposed one in red. And we look at instances of the size 200 to 400. And as you can immediately tell, the branch and bound approach in blue is just not good. It's a lot worse than the other two, so we can ignore it. And if we try to compare the state-of-the-art approach and ours, the situation is not really clear. So at some instances, the state-of-the-art approach is better. On some instances, we are clearly on some instances, we are clearly better, and some others, the state-of-the-art approach is clearly better. So this is the time to reach the optimal solution. If we now look at the time to reach a solution which is 1% close to the optimal one regarding the cost, the situation changes also for the simple branch and bound, but not much. And for the bottom up, as I said, it doesn't change at all because it only finds the one optimal solution. For our approach, on the other hand, the situation changes drastically. Like here, for example, the time to find a reasonably good solution drops by a lot here, especially for those larger instances. And as you can probably really tell what is going on here for the smaller ones, I just summed up the data in a small table. So this is exactly the runtime for the 9 instances, the time to reach 1%. And as you can see, indicated by the bold font, most of the time, so always but once, our solution is better or faster than the bottom-up approach, and it even beats it with a significant margin. So often it's like 20 times or even more than 50 times faster. All right, so to sum up, we proposed a new CP-based branch and bound approach for the degree constraint and spanning tree problem, where we improve each intermediate solution with an adapted LKH. It's significantly faster than the basic branch and bound, and it's competitive to the state-of-the-art CP approach. And finally, it beats the state-of-the-art approach when it comes to finding near optimal solutions quickly. Thank you very much, and I'm happy to take any questions.
Are there any questions in the audience? Otherwise, I would have a quick one. So your 1% from the optimal, is that from the optimal solution, or is that an optimality gap produced by your method?
This is from the optimal solution.
Okay. So without the optimal solution, you wouldn't know typically how far is your method, right?
So no, we don't have any theoretical guarantees. Yeah, it's just an empirical value.
Mm-hmm. Would be fun to do a primal dual method from the bottom up and your LKH.
Right.
Search.
Yeah.
All right. Any other question, last call? Otherwise, I'll defer everybody to the offline, to the individualized Q&A session for the coffee break that's about to start. Coffee will be served in your own individual kitchen, I guess.